Okay, thank you very much for the introduction. And again, thank you very much for the invitation to give a talk today. So yeah, as pointed out, I'm going to talk a little bit about sparse polynomial approximation, high dimensional functions. And today we're going to focus exclusively on doing this with random samples. And again, I want to give credit to a lot of collaborators that I've worked on over the last few years in this area. So here's kind of a outline of what we're going to talk about. So I don't need to give much of a motivation here to this audience, but originally we had started in this area working on UQ with sparse grids, and then since then gone on to look at other high dimensional systems. So I'll give a quick motivation and then talk a little bit about polynomial strategies in general, and then talk about sparse polynomial approximation. What I'm going to focus on a little bit today is this work we've done on weighted convex L1 regularization. And if I have time at the end, which I probably won't, but if I do, then I'll talk about a theory we've developed for non-convex regularizations in the same context. And I want to make sure I give credit to all the people who have sponsored me over this work. And a lot of this stuff is also part of a big institute, which is at the University of Texas. Okay, so here's the basic outline or the motivation of what we're going to do. We've heard a lot of good talks laying this out, but basically the idea is, and I'll try to use my mouse at some point, but the idea is we want to approximate a function. And here I've written it as a PDE model, and we've seen many examples here. So I want to approximate the map from a set of parameters. I'll assume they're finite dimensional, even though D can be very large. And we may be interested in a quantity of interest of the solution U, but in general, we're interested in the map from Y to U of Y. Okay. In general, we can look at this operator being linear or nonlinear. The point is that it depends on a set of D parameters. Okay, so I parameterize the function or the model itself. Purposes of this talk, I'll make two assumptions. One is that the domain is bounded, so it's a hypercube, and that I have a joint density in which I'll sample from. Also, I'm going to focus exclusively on the case where we have smooth polynomials. In other words, smooth functions. And in this case, I'd like them to be analytic. Of course, if I have a PDE model, then of course this enforces assumptions on the coefficients and the uniqueness and existence of solutions as a function of the parameter. And as I pointed out, so then our goal is to not only approximate the solution map from parameters in U to solutions in V, but I'd like this accuracy to be comparable to the best approximation. Okay. And again, I'm not going to talk about discontinuous functions at all in high dimensions. Okay, so beyond just UQ, this type of problems obviously come up in a lot of different applications. I won't go through them all. We've heard a little bit about optimal control, but there's additional ones that we've looked at, like neutron medical imaging, plasma problems, high dimensional Schrodinger equations, etc. And so one idea is that, to solve these type of problems, obviously, we can build bigger computers and etc. But again, fundamental limitations will always exist. In our case, what we're really interested in and why we started getting into this is rather than focus on high dimensional deterministic type sampling, we wanted to recover with best approximation accuracy without having to, one, acquire the solution map, and two, make the strategy as simple as possible. In other words, rather than coming up with some deterministic grid in high dimensions, we want to just randomly sample, but then still recover polynomials. So here's the basic idea. We've heard about variations of this throughout the talk. So I'll always use this multi-index notation for my polynomials in multiple dimensions. And so, in other words, I'm going to approximate regardless of the coefficients can depend on, obviously, They could just be complex valued, or they could be even function valued themselves. And so I'll have an approximation, I'll call u lambda, and that's nothing more than a sum over these multi-indices in some set lambda, which I'll define in a minute. So the advantage here is that we're going to, well, in this case, we're going to take advantage of smoothness, and in addition to that, sparsity of the function itself. And the idea here is that even though we're going to enforce random sampling, we still want to recover the polynomial with accuracy, like I said, equivalent to best approximation. In other words, we should be able to prove that we get faster convergence than Monte Carlo in general. The challenge, of course, is, as pointed out, the computation of these coefficients will require at least the cardinality of the index set in high dimensions, and this is where the challenge comes in. And again, the efficiency of these approaches will heavily depend on the selection of this index set. Okay, and in general, this is done a priori, but in nonlinear type methods, this is done essentially constructed on the fly. And so, again, just point out that the coefficient could be complex valued, or in more general, it could be function valued, or say, for example, in the PDE setting, or at least the simple PDE setting, this could be, say, H10. I'll always assume throughout today's talk that this is an orthonormal system, and in fact, it's a bounded orthonormal system based on the assumptions. Okay, sorry. So here's the kind of standard way that, we've even done this in the past, where, we will attempt to a priori define, say, a closed or a downward closed index set, knowing that the challenge is that the cardinality of this set can grow quickly with respect to dimension, in fact, typically exponentially. And as pointed out throughout many talks, here's just some examples of the polynomial index sets themselves that are typically used. On the other hand, what we want to do is that, remember, I'm focused on the finite dimensional setting. So we want to construct some optimal set, in other words, a set of the S most effective indices that guarantee the best approximation error. In the finite dimensional setting, we've worked on this in the past and proved that the rate of convergence of the best approximation converges in the following sense. I won't go through the absolute details, but say, regardless of the scheme you use, you cannot fight the fact that you still will encounter a d-th root of the dimension, but you are, in the sense, exponential in S, and so you're fighting this 1 over d here. And this is available in this Numerical mathematique paper, the details of the proof. Okay, so obviously over the past, say, 4 years, we've been working quite a lot in this area with various collaborators. So what I'm going to do today, and I'm just pointing out the papers in case you're interested, is that, like I said, I'm going to focus on a completely random sampling strategy. And then I'm going to show you that, we can recover both, say, complex valued, Hilbert valued signals in this particular setting. I'll show you how to recover the number of samples required by L1 minimization to guarantee that best approximation. And then I'll show you, I don't like using words like overcome, but at least a specific choice of weights to kind of fight that curse of dimensionality that will show up. And as I mentioned, there's several papers on this, and there's a recent book we put out on this as well. And then I'll show you that, as I mentioned, that we can extend this theory to, say, mixed energy norm-based regularization of a PDE. In other words, we'll reconstruct the joint sparse signal over, say, mixed space. And again, if you have, say, an elliptic problem, this is H10 mixed with L1, okay? And then there's some corresponding papers that go with that. And as I mentioned, we've also looked at regularizing with non-convex minimization type problems. And we're able to develop a theory that shows in what cases these non-convex minimization problems that people have looked at are at least as good as L1. And there are several papers there as well. Okay, so the basic idea here, let's just go back to signal reconstruction. And the idea is that you want to recover a function or signal from an underdetermined system, say of the following type. And the assumption here is that we have only a few coordinates that are non-zero. And this is where the sparsity comes in. In other words, if I refer to something as an S-sparse vector, I just mean a vector with at most S non-zero entries. Okay. And then again, there's, various sparsity induced norms that people have looked at. Of course, we'd like to use an L0 minimization, but of course, this is NP-hard problem. So then people have looked at, say, non-convex regularization, say of the type L1 half. Of course, this is again, very complex type problem to solve. If we have time, we'll talk about this. The obvious one is to do, say, L2, in other words, a least squares type approximation, again, where the minimum solution lies on the tangent to the L2 ball. The reason why people enjoy L1 minimization, or at least utilize L1, is because one, it's a convex regularization, and the solution to the minimization problem is nothing more than the point at which the L1 ball meets the line, X equals B. And so reconstruction in this setting is guaranteed with high probability. I'm going to use random sampling. And in this case, I'm going to focus exclusively on uniform recovery results. In other words, I want success with a high probability for all S-sparse vectors, as opposed to the non-uniform case, which is when you're interested in success for each fixed S-sparse vector. Okay. So the basic setup is quite straightforward, and then I'll show you how we arrive at the minimization problem. So again, recall that I've written the polynomial approximation. I've simplified it here as the following way, and the goal here is now I'm given some random, or I'm given an index set which could be far from optimal. Call it lambda 0. In other words, the cardinality is n, and it could be much larger than S. And I'm going to then reconstruct that function approximation. The idea to set up the problem, in other words, the compressed sensing type problem, is I'll sample according to the orthogonal measure, that orthogonalization measure I've written down earlier. I then construct a matrix A, which is nothing more than those basis functions evaluated at the random points. This constructs the entire matrix, and the data is nothing more than this function itself, or the solution sampled at sets of random points. The coefficients then are, in the case that I'm just looking at complex valued reconstruction, it's then this solution of this linear system. However, as I mentioned, I want to construct the approximation to be comparable to the best S term. And then this will require the number of samples to be on the cardinality, or at least on the order of S, much smaller now than the cardinality of the index set. In other words, this system is underdetermined. How one solves this, obviously, is using greedy type algorithms, thresholding, or in our case, we're going to focus on optimization. Okay, so the solution here of the S-sparse vector I've denoted C. And again, I have these measurements which come from some high dimensional system, if you recall. So the unique sparse solution to this matrix problem is nothing more than the minimization, as I mentioned, in L0 subject to this constraint, right? In the case that C is sparse, obviously this is the norm we didn't like to induce, but as I pointed out, it's an NP-hard problem, and it's in general due to the non-convexity of L0. And if I want to look at something like L2, then I'm going to require the number of samples to be larger than the cardinality of n. So another way to think of L1 is that somehow is splitting the difference. It's a convex regularization, but splits the difference somehow between L0 and L2. And I'll say a little bit more about that as we go. Just making sure I'm in order here. Okay, so uniform recovery typically, and I'll say something about this again at the end, but in general is guaranteed by what's called the restricted isometry property, or the RIP. And it's of the normalized system here. I'll denote that as A tilde. And the matrix or the normalized system satisfies the RIP. In other words, if there exists some delta, I'll call it delta S, such that for all S sparse vectors, the application of that normalized matrix to the S sparse vector Z can be bounded above and below by something close to the vector itself in L2. The intuition here is that if I look at the kernel of the matrix A, it doesn't contain any non-zero S sparse vectors, okay? In addition to that, one can show that the RIP implies the null space property, which is in general the necessary and sufficient condition for recovery of the best S term approximation. And one can show quite easily then that if I have a matrix A that satisfies the RIP, then in L1 I can bound this by the best S term approximation, which I've denoted here as lambda S, or sigma S, sorry. Now, the challenge then is, how does one estimate the number of measurements to guarantee that the RIP is true? Okay. And so this is where we really got engaged in this area, not just in the high dimensional case, but even in the signal processing case. And so when we originally sat down and looked at this, we were convinced that the current theory could be improved. And there was kind of a three-stage process that we wanted to go through. So the first one was there are always logarithmic factors in these type estimates. And we were convinced even the most recent work could be improved by at least a factor, at least one log factor. In addition, it bothered us that in general, all of the results depend quite heavily on this mutual coherence term. And in this case, theta here is the soup of the basis functions. So in one dimension, this is not a big deal, but in multiple dimensions, if I was to apply, say, a Chebyshev polynomial, this grows exponentially in D. Even if I precondition, say, a Legendre system, it's still exponential in D. And the Legendre system in general grows like the cardinality of that index set. So one is, how do you overcome this issue? The second one is then, or in addition to this, is that I am in multiple dimensions. So can I optimize the cardinality of that index set? In other words, is there a way that I can even speed up like MATVEC multiplications by optimizing this cardinality? So the result, which was shown actually in 18, it was actually a paper in 18, this is a typo, is that if I have now this matrix, random sampling matrix, which is again associated with this bounded orthonormal system, then you can show that the complexity or the number of samples required, as you can see, depends quite heavily on this mutual coherence term. This is the improvement of the log factor, but you're still fighting a log factor in the cardinality of that set. But anyways, the point is that with M samples, at least of this order, then with high probability, I can guarantee the RIP is true for some delta S less than delta. Okay, as I pointed out, this is the current best available estimate, which improved the log factors from a set of papers, very impressive papers. And the proof itself is true for any bounded orthonormal system. And the way that we achieved it, I won't go through the details, but there's a chaining argument which we used, which is, in other words, in our opinion, was fundamentally different than the ones presented in the past. And you can take a look at this paper to see the details. Okay, so the second thing that we mentioned here is that I wanted to reduce the dimension dependence on the mutual coherence term. And the idea for us was, in the case of parameterized PDEs, at least smooth functions, the set of S terms are often defined by, say, an approximate lower set. So what we then decided to do was, can we reconstruct a function which is comparable to, say, the best lower S term? In other words, the best approximation by S terms forced in a lower set. One can show that this best lower S term is just as good as the best S term approximation. Obviously, if this is true, then the sample complexity can be reduced. And how we start this procedure is that we're looking at the union of all lower sets, which can be shown to be hyperbolic cross, which is given here, the cardinality of which has been estimated in several papers in the past, but this is, I think, the current best available estimate, which grows like S cubed 4 to the D, which you'll see why this can be helpful for us in a second. Okay, so to focus on the best S-term approximation in a lower set, we modified the definition of the RIP to include something in which we call the lower RIP, which looks very much like the standard RIP estimate, except we want this to be true for all Z sparse vectors that satisfy the following constraint. In other words, if I take the sum of the basis functions in L infinity, I'll call that K tilde. I want K tilde of the sup of those vectors to be bounded by this term K of S, which is nothing more than the sup of K tilde, where I've enforced the fact that lambda is lower with cardinality S. The advantage of this way of looking at the problem this way is that one can show that this lower RIP is a special case of something called the weighted RIP, which was introduced in this Rahud and Ward paper 15. The advantage is that by doing this, our procedure induces a specific weight. In other words, the weight itself is induced by this lower RIP is the L infinity norm of basis functions itself, which we were able to show actually in a sequence of papers that this is the optimal selection of weights. Okay, if I go through now the theory induced by this lower RIP, you can see that the sample complexity looks exactly the same, except that wherever I had an S, now I've replaced it by a K of S. In other words, with high probability, given this number of samples, this matrix will satisfy the lower RIP. Now, in the case of several examples, we can take advantage of estimates of K of S. Let's pull this back. And show that if we utilize the estimates for K of S, which were shown in this paper from 15, and the bound of the hyperbolic cross itself, then we can show that if we force a Chebyshev basis, then the bound or the minimal number of samples required then grows like a log 3 over log 2 or S to the log 3 over log 2. And then we still maintain this log squared term, but we also pull out a log S plus D. In other words, the number of samples now depends, of course, up to a constant linearly on dimension D. And even the case with Legendre, even though we get a growth of S squared, we still maintain the same log factors. Okay, now the strategy itself, remember, I focused at this point only on complex valued functions. So just high dimensional functions themselves, but the recovery strategy is quite straightforward. Remember, I've given you a choice of how to specifically choose this multi-index weights. I then have a function f I'd like to approximate. I've given, just define for you the weighted L1 norm, which is given here, which is nothing more than the sup, assuming that this should be f. This is correct. The inf over the sup of G is lower, and its cardinality is S. So the procedure then, or at least the algorithm, is again straightforward. We choose those weights. We construct a sampling matrix. If we have a tail estimate, then we'll utilize it. I then want to reconstruct this function U sharp, which is nothing more than the solution, or the coefficients are nothing more than the solution to this minimization problem. Okay, so here's some simple examples. I won't go through the details of the setup, just say that we use this SPGL1. It's a spectral projected gradient approach. In this case, I'll fix the cardinality of a hyperbolic cross set just to show you how this works, increase the number of samples up to a maximum. In each case, we fix the seed of the number generator for each choice of the weights. And then we'll run, say, 50 trials just to show you what it looks like. In all examples, I'm going to focus on Legendre expansion. So in our case, in other words, what we propose as the optimal weight is given here. Okay, so here's a simple function in 8 dimensions where we'll show that here's the magnitude of all the coefficients and then sort it so you can see the decay is quite fast. But in other words, if I'm in D equals 8 dimensions, my cardinality of my index set is about 1800. And as I mentioned, this is just the coefficients. Okay, so here's what things look like. So if I take, so here I'm plotting, and this should be F minus F sharp, but we're plotting the expectation in L2. This is just the number of samples divided by the cardinality of the index set. And now I'll show you that if I use a standard L1, here's the convergence of standard L1. I'll then increase the weight, even though I mentioned to you that the proposed optimal weight is given here. And you can see that I can continue to increase this weight in L1 and it doesn't really buy me anything, which is what the theory projected or predicted. Of course, this should work better if I go to even higher dimensions. So let me take the same function in now 16 dimensions and show you how things perform. And as you can see that again, I'll continue to increase the weight where again, this is the weight that we suggest one should use. And you can see regardless of the increase in weight, I buy nothing. Okay. Okay. So now the idea then is how do we extend this to the case of parametric PDEs, or how do we reconstruct the full solution in this setting? And even though the problem becomes obviously harder, the setup is again, quite straightforward. So again, I'm given this same setup as I had before, except now I'm going to rewrite the problem in the following way. I still have this multi-index summation, but then I've added in a function which sums over R, and you can think of this, say, as a finite element type basis. Okay, if I'm doing, say, a finite element approximation to a PDE. Again, sample the M samples of the random variables y of k. Again, now for a fixed R, I can then construct the sampling matrix as before. And then again, I have for fixed R, I have the high dimensional data, which is then again a vector, but then each one of these will itself be a countable solution to, say, the PDE problem. The coefficients solve the same problem, except here the data itself, again, is a matrix in CM cross N itself. And so one can think of this problem as a very special case of joint sparse recovery, but the challenge or the additional challenge is that these vectors themselves have countably infinite length. Okay? In other words, say I have a basis for that Hilbert space, so I have not approximated that solution yet. Okay, so in this case, again, we'll modify the RIP constraint. And again, the setup is the same, except now I want to reconstruct a function, but I've given these what we'll call this VRIP, which is nothing more than the modified version of the RIP, except now I have a mixed norm VL2. And under this condition, if a matrix satisfies the standard RIP, then it also satisfies this RIP with a change of this delta term. The complexity also recovers over to this case. And then if I want to then reconstruct Sorry. If I want to then reconstruct the function or approximate this function by U sharp in L2, I get the following bound. I eat a square root of S, essentially because I'm doing the estimate in L2. Okay. There are several numerical algorithms, of course, for computing type these type problems. The typical or the most popular ones are Bregman or forward-backward iterations. In our case, though, we have to modify these type algorithms because recall that we're approximating over this function value space. So if I then modify, the modification is straightforward. The theory is not, obviously. In this setting, we were able to show that we get strong convergence, at least in the forward-backward iteration, even in the infinite dimensional case. Previously, all that was shown was there's finite convergence shown in these papers and weak convergence shown in this Dobeshay and Combet's papers. And again, we were able to extend this to show that you get strong convergence, at least in this case. We're working currently on the Bregman iteration case. Okay, so here's a simple problem we've seen ad nauseum over the past 20 years, I guess, or at least 10 years. And so here's an elliptic problem. I'll assume that my domain is just, I focus on samples from a uniform distribution. The coefficients are related to, say, a Fourier expansion of exponential covariance. Here, L will denote the correlation length, and A min, of course, is going to be chosen to guarantee that we have coercivity, etc. Okay, so here's just a simple result. So we have now A being an affine coefficient in at least 100 dimensions here, where we have a pretty reasonable size correlation length of 1/4. So we have a lot of active dimensions. I'm going to start with thetas or gamma 0 being a total degree space. I have polynomials of order 2. In other words, then the cardinality of that set is about 5,000. Again, the weights are given as the following. So here what we've done is several things. So one, we've plotted the Monte Carlo convergence to this problem and then just showed you the order of convergence we expect. And then we went ahead and also computed a sparse grid approximation using, say, Chebyshev points, and then even a Galerkin approximation using a total degree subspace, just to give you an idea of the convergence. Of course, this is in 100 dimensions, so running this any further with such deterministic approaches, it's not feasible. However, then we take the same samples used in the Monte Carlo approximation and we use the weighted L1 approach, and then you can see the advantage of the compressed sensing, given that we're still constructing using completely the exact same random samples as the Monte Carlo approximation. And you can see it gives you pretty impressive results, even in this type problem. Okay, how much time do I have left?
About 10 minutes.
10 minutes. Okay, so maybe I'll try not to go too quickly through this. It's very theoretical. Okay, so up until now we focused exclusively on a convex relaxation of the L0 problem. We'd also wanted to see if we could develop a supporting theory for non-convex, because there didn't seem to be much outside of iterations on LP, say P is less than 1. So in general, there's been many numerical papers that have shown if one uses various non-convex regularizations, then you can show, or at least numerically, that they are better than L1 at enforcing sparsity. But this has really not been observed in theory, so we'll say a little bit about that. Previously, so there are theoretical guarantees, and in general, these are established through various versions of null space properties, which was originally introduced in this Cohen-Dama-DeVore paper from 2009. theory does exist to show that certain LP approximations, P less than 1, are less restrictive than L1. But in general, we've seen things like more restrictive approximations in L1, like 2-level L1 or L1 minus L2. There's numerical results, but not theory to explain these. In addition, there's really not available anything on, say, what people are called capped L1 or sorted L1. And I'll show you in a minute what these look like. So the theory here will include a lot of non-convex regularizations. It does not include what people would call L1 over L2. We have a separate paper on that. Okay, so let me just see here if, yeah. So I won't go through the details here, but just say that I'll mention here that I'm going to rewrite the regularization problem or the compressed sensing problem in the following way. I'm now going to minimize this non-convex function here, I'll call R of Z, subject to the same constraint. And R here is a mapping from Rn to 0 infinity, given in the following way. I'm not going to say anything about concavity symmetric increasing, other than I'll mention this in the theory. So the theory then that I'm going to show you will include all the following type examples. At least they'll fit into the theory. So LP with P less than 1. There's already a paper there are several papers on this particular one, but our theory will also include this. It includes L1 minus L2, what people call capped L1, 2-level L1, sorted L1 in the following sense, the transformed L1, and even this method people have called SCAD. And I'll show you some examples of the LP balls here. So here's the L1 half, which we showed you earlier. Here's the L1 minus L2 ball. Here's the capped L1 ball and what people call 2-level L1. And as you can see, the goal here is to get as close as possible to L0 or something intermediate and see if one can reconstruct with accuracy better than L1, or at least enforce sparsity. So as I pointed out, the necessary sufficient condition for reconstruction of every S-sparse vector when I use L1 is it utilizes the null space property. So the null space property, if I have a matrix that satisfies the null space property, then the kernel can be contained in what I'll call this NL1 set, which is nothing more than I have the bound of a vector I call VS in L1, and it's bounded by a vector in the complement. And this is true for all sets of cardinality less than S. And the RIP, as I mentioned, implies the null space property. So there's been several RIP type estimates developed. Unfortunately, what they show is that such methods are stronger, in other words, more restrictive than the null space property. And so we wanted to understand if this can be improved. So there's been some work on 2-level L1, and what was shown is that the kernel is contained in a set of the following definition, which won't go through the details, but say that the set itself is not properly contained in the L1 null space. In other words, this is more restrictive than L1. And the same can be said for L1 minus L2. And so there's not really a theory to support why this would enforce sparsity at least as well as L1. And so what we were able to do is show the following, that if we look at a more general class, at least encompassing what was all above, then one can show that the sparse recovery is at least as good as L1. And in our case, we show that the null space condition is more than sufficient. And how we do this is that we end up with a weaker property of the following type, that our kernel is contained in a set where you can see that it's not just strictly contained, but less than or equal to contained, or bounded, I'm sorry. The basic idea is that we prove that if we have that non-convex function, that it can be bounded by a function that's modified by a vector in the kernel. And I'm not going to go through all the details here, but when we want to show this, we have a combination of what we've called the null space property with this what we then called this INSP, or in other words, the non-convex set, or other words. The nice thing is that we've transformed this problem into an inequality estimation problem, and therefore we have no need to further inspect the kernel. And let me just kind of lay out the results, even though they're somewhat complicated. So again, I want to minimize this function subject to this constraint. If I have a function that is symmetric, concave, and increasing, and the following is true, then this approximation is at least as good as L1. In other words, every S-sparse vector is the unique solution to this if the kernel is contained in the L1, in this set in L1. Now, the nice thing about this is applicable to all the previous non-convex penalties. And when we look at sorted L1, we need an additional condition. But this tells us that all of those non-convex approximations are at least as good as L1. But the following result tells us which ones are better. So if I have a stronger condition, again, I still have a symmetric concave increasing function. If I replace this by a stronger condition of the following type, then one can show that this approximation is better than L1. In other words, every S-sparse vector is the unique solution if that kernel is contained in the set that we proposed earlier. This is applicable to LP with P less than 1, which was verified in a different set of papers. It's also true for L1 minus L2, sorted L1, or this transformed L1. And I think with that, I'll just finish up and say a few things. So at the end, I did show you this null space, unified null space condition for class of general non-convex minimizations, showing they're at least as good as L1 and which ones are better. When we went through this idea of weighted L1, I tried to show you these guaranteed recoveries that can combat the curse of dimensionality. And the idea, again, was we exploit the structure of the best S term approximation. We utilize this improved estimate of the RIP. And the nice thing is, as I pointed out, we can recover the true best S term approximation and not say a weighted version, which then requires a weighted version of the Stechkin estimate. And we've also shown that this query complexity carries over to the Hilbert value case, or even Banach valued recovery. And as I mentioned earlier, we are extending the notion of this, the fixed point continuation and Bregman iterations to this Hilbert value case. And just let me say one last thing about the RIP. So, I stole this statement from Terry Tao, that is that let's try to let the RIP rest in peace. And we were able to then show that in a different set of papers, something interesting. So it was shown in the following, it was shown in the following papers that sufficient condition for reconstruction of S-sparse vectors, as I showed earlier, can be bounded, or is at least the size of the mutual coherence times these log factors. So what we did was, again, this is all based on the fact that you have a uniform bound for the basis function. So what we looked at is then, rather than taking a uniform bound of, say, Legendre polynomials, let's look at the envelope bound of Legendre polynomials, combine it with something known as restricted eigenvalue condition, And then what we're able to show is that this restricted eigenvalue condition also implies a robust version of the null space property. In other words, the upper bound to the RIP is not necessary in this case. Consequently, what we can then show is that the number of samples is at least grows of the following factor. In other words, the number of samples can be at least the S squared times log factors, and we've completely shown this is independent of the mutual coherence. Unfortunately, this is great in say lower dimensions. We are not at this point able to recover the multi-dimensional approximation using this, but at least in the small dimensional case, we're able to remove completely constrained on mutual coherence. And I don't like to do this, but I'll finish with just a quick advertisement for our recent book, kind of along the same vein. Sparse approximation for high dimensional functions. It's available now, and there's a company website where we've already started to put up all the errors in the book. So take a look there if you take a look at the book. In any case, that's it. So I'd gladly take any questions.